All right, this is a little extra video here that is optional for AP Physics this year because of the change in the exam. But this is something that I did, we were working on right before we left, and this has to do with thin film interference. So we talked about the crazy colors in the soap bubbles. And here comes a light ray, reflects off this surface, and then there's the one that refracts. I did not draw the refraction because it doesn't matter when this thickness is when the distance d there is very thin, the geometry doesn't matter. Okay, and then we get the reflection off of here. So the ray that reflects off here and the ray that reflects off here, and then if our eyeball's up here, we can get those crazy colors depending on the destructive and constructive interference for various wavelengths. Now, the wavelength coming in up here where we observe it and where it's out here is the original wavelength. And then we have the wavelength in the medium. And right before spring break, we had done everything in terms of wavelength in the medium. I'm now going to show you how to write those equations in terms of the original wavelength. Okay, so there's some algebra to back up why. And you should be able to, if you're watching this in future years, if I share it, you should be able to do it for AP tests, not counting this year's, okay? But I do want to show you guys this in terms of the original wavelength, because when we have the light that goes into here, there is a shift in wavelength because we have a change in the speed of the electromagnetic wave, the light, in that medium. Okay, if it's like air, water, air, it slows down. Let's just go ahead and call it like air, water, air kind of thing, like with our soap bubbles or soapy water. Okay, all right. So we're going to go ahead and remind you guys here that the index of refraction is a ratio of the speed of light in a vacuum over the speed in the medium, And I'm going to call this N1, and I'm going to call this N2. 1 is where we're starting, 2 is where we're going. And what we're really trying to do here is get this equation in terms of wavelengths. And I'm going to use a ratio and also the idea that we've got another big equation here that V equals lambda F. Okay, so those are the two ideas I'm going to combine to figure out, well, how do I write my wavelength in terms of the original instead of in terms of the wavelength in the medium? Okay, so I'm trying to relate these two lambdas. Okay, so I'm going to start by relating the two n's. All right, so I'm going to, in this case, I'm going to say N1 over N2 equals C over V1 over C over V2. And remember, C is the speed of light in a vacuum. So I'm just going to go ahead and cancel that out. And I'm going to rewrite this. We've got some improper fraction nonsense going on here. So this V2 will flip up. This V1 will stay in the denominator. So I'll get that, V2 over V1. Now I'm going to substitute in for my V's. I'm going to substitute in wavelength. Now this is, I called this 2. So to be consistent up here, this is the speed at spot 2. That's when I'm in the water. So I'm going to call that the wavelength of the medium, okay? The wavelength in the water in this case, okay? Times the frequency, F. Now here's the thing you got to remember, okay? And this is actually, could still be relevant. Yes, this is still relevant for non-optic stuff. When you go from one medium to another, the frequency for the electromagnetic wave has to stay the same. Because that will eventually, in our modern physics stuff that's not tested on this year, will be tied to the energy of the electromagnetic wave. Okay, so the frequency is the thing that has to stay the same. The wavelength and the speed can and often do, if it's a different medium, different index of refraction for light, it will change. Okay, so lambda m f over, now for V1, this is in the air, so this will be the original wavelength, okay, times that frequency. So the frequencies will cancel out. So I'm left with here that V2 over V1 equals the wavelength of the medium, like in the film, divided by the original wavelength. Okay, so if I want to get rid of this, I'm trying to get rid of this in my equations for thin film interference, I'm going to solve for that. Okay. Wait, why did I substitute in? Oh, yeah. I had to get lambda in. Yeah, we're still good. Okay, so let's keep going. Because right now it's going to be in terms of V. We're going to have to go back to terms of N. All right. So let me go ahead and rearrange and solve for that. So I'll get wavelength in the medium equals the original wavelength times V2 over V1. Okay. And then I'm going to add an equation up here, just rearranging that. V equals Cn. All right, hold on a second. multiplied by V, multiplied by V. How about we do that the right way? V equals, so the V's over here will cancel out, okay? Multiplying both sides by V, and then V will equal C divided by N. There we go. I knew that was wrong as soon as I wrote it. V will equal C divided by N. So I can go ahead and substitute back into this equation because I don't want it in terms of V, I want it in terms of N because that's usually what's given in the problem. All right, so we'll go ahead and now do some additional substitution. So the wavelength in the medium will be the original wavelength times, I'm going to apply this for my 2, which is when I'm in the water here. So I'll have C over N2, C over N2 over, and then I'll have C over N1. The C's will cancel out again. Flip these around. So I'm going to get wavelength, and then I'm going to move over to here now. Wavelength in the medium equals the original wavelength times, this will flip up, N1 over N2. And there we have it. That's the end result of this substituting a couple times with our equations. Okay. So if you want to get rid of this in a thin film interference equation, you just write the original wavelength times whatever your N1 was divided by your N2. Now, a lot of times, but not always, you could be starting in air. So sometimes people will remember, well, if the light's starting off in air, I just divide by the index of refraction of what I'm going into. So that's fine. So a lot of times you'll see like just it written as like lambda naught divided by like 1.3 or 1.4 or whatever. And that's what you'll see popping up in some of those equations. That's just because N1 was 1. Otherwise, it would be something over something times the original wavelength. Okay, so that's how you get these in terms of the original wavelength. That's it. Again, not on this year's test. All right, let me spin this around here. That's probably very disorienting. Hopefully, I might cut that part. If not, just deal.